Here we have to find out the collector voltage. In order to find out the collector voltage, we need to know the collector current. In order to know the collector current, we need to know the base current, which is given as follows. Here VBE, whose value equals to 0.7, VE equals to VB minus VBE equals to 4 minus 0.7 equals to 3.3. IE is equals to VE by RE. VE equals to 3.3 divided by 4K equals to 0.825 milliamps. We are assuming IE is approximately equals to IC. Hence, VC equals to VCC minus ICRC. 8 minus 0.825 into 5K equals to 3.9 volts. Answer option B. We have to find out maximum sine wave output voltage possible at the output of an op-amp which having a slew rate of 10 volts per microsecond. Suppose assume the output of the op-amp V0 equals to V sine omega t. The slew rate is defined as follows: dV0 by dt. From this, d by dt V sine omega t is equals to V omega cos omega t. dV0 by dt max equals to V omega, whose value equals to 10 volts per microsecond. From this, V equals to 10 divided by 10 power minus 6, 2 pi into F is given as 10 power 6, 2 into 10 power 6, whose value equals to 0.8 volts. Answer option A.
The given limit is, limit extends to 0, sine of pi cos square x by x square. We have to evaluate this limit. Now, limit extends to 0, sine of, I'll convert this cos square x into sine square x. Cos square x can be written as 1 minus sine square x by x square, which can be written as limit extends to 0, sine of pi minus pi sine square x by x square, which can be written as limit extends to 0, sine 180 minus theta is nothing but sine theta, which is sine pi sine square x by x square. Now, we know limit theta tends to 0, sine theta by theta is always 1. So, if it is theta, it should be theta now. Look into the function here. Theta is nothing but pi sine square x. So, even in the denominator, it should be pi sine square x. So, we will multiply and divide by pi sine square x. Then the limit will be limit extends to 0, sine of pi sine square x by pi sine square x into x square into pi sine square x. Now, I'll write it as limit extends to 0, sine pi sine square x by pi sine square x into limit extends to 0, sine x by x whole square. Now we know limit extends to something, f of x into g of x will be equal to limit extends to something, f of x into limit into g of x. Now, we know sine theta by theta is 1. So what will be this function? 1. So what will be this limit? 1 square, and we are left with this pi. So the answer is pi. That is option B.
question is, we have to find out the derivative feedback constant for a given transfer function whose damping ratio is 0.8. If we compare the transfer function with the standard transfer function, we are going to get natural frequency equals to under root 25, which is 5 radians per second, 2 zeta omega n equals to 4. From this, zeta equals to 0.4. Damping ratio with derivative feedback control is zeta dash equals to zeta plus natural frequency omega n derivative feedback constant kt divided by 2. If we substitute the above values, 0.8 equals to 0.4 plus 5 into kt divided by 2, kt equals to 0.16, which is the option B is true. In the above problem, we have to find out the steady state value of the above given expression. That means from the final value theorem, limit t tends to infinite, f of t is equals to limit s tends to 0, s into f of s. But the problem with the above final value theorem is that it is applicable only to the stable systems. That means final value theorem is not applicable to the systems whose poles lies on j omega axis or right half of S plane. For this particular problem, poles are located on j omega axis. Hence, final value theorem is not applicable for this problem. Hence, steady state value is not defined.